I'd like to start off today by doing some review from last time. So I want to see about how folks are thinking about some of the ideas. I think I'm going to start doing more of this. We're following up each day's lesson with some questions at the beginning of the next day so that I can see how people are doing with the ideas, how much retention there is either 2 days or 5 days later. Okay, so let's start off with a question about a definition. So suppose that V is a subset of Rn for some n. What does it mean to say that V is a vector space? Okay, so if you folks are giving the kind of standard linear algebra definition, that's good. I think that's a perfectly satisfactory definition. Yeah, so Hardy, do you want to tell us about yours? This is a nice articulation of it. Yeah, exactly. So this idea of being the term that's often used in a linear algebra class is closed, meaning that if you have a vector in V, it has to be the case that any way you can scale it, what you get is still in V. And similarly, if you add any two vectors in V, is still what you get is still going to be in there. So several folks were kind of focusing on this n dimension here. This is given, right? So this first part of the sentence, it's saying, suppose that V is a subset of Rn. That means that the elements of V are going to be lists of n real numbers. That's just part of the setup. The question is, what does it mean to say that V is a vector space? So some subsets of Rn are not vector spaces, most in a certain sense. Some subsets of Rn are vector spaces. And so the question is, what's the difference between the two? How do you tell the difference between something that is or isn't a vector space? And the important idea is that you ought to be able to perform vector space operations, namely scalar multiplication and vector addition, without leaving the space. So if you can add or add two things in V or scale something in V and get something that's suddenly not in V, then that's no good. That means V is not a vector space. And the definition that we gave here last time, which is a little more succinct because you don't have to talk about what it means to be closed, is just to say that V is a vector space if it can be written as the span, in other words, the set of all linear combinations of some set of vectors. So if you take like a couple vectors and take their span, that's going to be a plane. The generalization of that idea, any number of vectors you want to take, whatever vectors they are, take their span. The resulting thing is a vector space. Conversely, if something is a vector space, then it will be the span of some collection of vectors in it. And I just mentioned here this other one, which a couple of folks also mentioned we talked about just now, that has to do with the vector operation. So these two definitions are equivalent. All right, let's practice this one step more with a multiple choice question. So which one of these four is not a vector space? Okay, so I put this one in because we don't talk about this one as much, and it's kind of helpful to think about. A circle around the origin is the correct answer here, though. A single point at the origin is actually a vector space because it's the span of the list containing only the zero vector. Because if you think about all linear combinations of the zero vector, you can't get away from the zero vector by scaling it or adding it to itself. You're kind of stuck there. So that's the zero-dimensional vector space. Then a one-dimensional vector space would be a line, two-dimensional vector space would be a plane, and a circle is not a vector space because if you have a point on the circle, you can scale it to get points closer than the circle, or scale it in to get points closer to the circle, or scale it out to get points further away. And all those points would have to be in your vector space because however you got to that point, you could have just used, a bigger weight or a smaller weight, or collection of weights rather, and you could get to those other points. So a circle around the origin is not a vector space. Okay, so here's another one we talked about last time. Suppose that we have a list of vectors in a particular vector space V. What inequalities pertaining to the length of that list are implied by its status either as a linearly independent list or a spanning list or both? So if you have one or the other or both of those pieces of information, in each case, what can you say about how long that list of vectors could possibly be in relation to the vector space V? Yash, do you want to summarize this for us? Great, nice job. So yeah, so that's something we talked about last time. So just to summarize here with this message, so if a list spans V, there must be enough vectors. In other words, there must be at least the number of vectors equal to the dimension of that space. If it's linearly independent, there can be no more than dimension V vectors, but there could be fewer. And if it's both, then it has to be greater than or equal to and less than or equal to. In other words, it has to be equal to. So a set that, a list of vectors that spans and is linearly independent is a basis, and it has to have dimension V vectors in it. There's this other case that we didn't talk about, which is if you're linearly dependent and you fail to span V. And here you can't say anything about how many vectors are in the list, because you could just have, let's say, 2 vectors and they both run in the same direction, or even just one vector that happens to be the 0 vector. That already constitutes a failure of linear independence. And there's just one vector. On the other hand, you could put more and more copies of the 0 vector into your list, or more copies of a single vector that's non-zero, and you would have, if it's a higher dimensional vector space, it wouldn't span the space, but you could have as many entries in that list as you want. So you really can't say anything in that case. Okay, here's another question about types. We had one of these last time. So if we're going to talk about whether L, some object, is linearly independent, what kind of mathematical object does L have to be in order for that question to make sense? Okay, so I'll share a few answers here. So is it Yunkyong? Again, just correct my pronunciation. I'm sure that I won't get many of these right the first time. Do you want to talk about why it's a list of vectors here as opposed to a set of vectors? Yes, exactly right. So a few people said a set of vectors. That's very much along the right lines. That might have been the term you used when you took a linear algebra course. If so, it's not quite right. That's an unfortunate thing about linear algebra courses. They just are cavalier about that term. I think if you want to rescue it, you have to say that when you talk about sets of vectors in a linear algebra course, you're sort of casually using the word as a synonym for list, because the distinction really matters. In any case, the most important idea here is that if you want to talk about whether something is linearly independent, that thing has to be a collection of vectors, whether you call it a list or a set. It can't be some other thing, like a geometric object. We're using lists of vectors as a way of describing geometric objects, but they're different things. One is, well, a geometric object, a collection of points in space, and the other is an ordered list of vectors. Like you can write it down explicitly if you want, as like, each vector is surrounded by square brackets and has numbers in it, and they're separated by commas. You can also think of it as the set of columns in a matrix. It's just a tidier way to write it down. But it's really important when you're thinking about vocabulary in any kind of mathematical or programming context to understand what kinds of objects things are, because it affects how you can interact with them. And it tends to get very confused when you start mixing vocabulary and performing certain operations on objects that don't support those kinds of operations and are only sort of related. You want to get those relationships really clear in order to make sense to other people and to organize the information in your head. So I just want to answer this question that came in. So why can it be a set of vectors? Because there's this issue with duplicates. So it can't be really. You have to stretch the notion of what a set is. We often say, you've heard me say it, you've heard other people say it, it's very common shorthand, these vectors are linearly independent. And that is fine if everyone understands that what we mean is the list of vectors consisting of these particular vectors is a linearly independent list. And the reason the vocabulary is a little sneaky is it sort of makes it sound like linear dependence is just some attribute of a vector, like, colors in the real world. You can have like a blue car or a red car. And if you say these cars are red, you mean for each car, that car has the red property. And of course, linear independence doesn't work like that. It's a collective property. So it would be more like, with colors, sort of these colors have the same color. That is a set level or a list level property rather than a property of each individual car. You can't look at one car and check off, is it same color or not? You have to look at them in aggregate. And same idea with linear independence. Okay, here's another review question. It's very similar to one we did last time, but it's slightly different in a way that I think is instructive. So I want you to find the coordinates of this orange vector with respect to the two teal vectors by just adjusting these weights however you need to. You'll see when you start adjusting the weights that you get this orange sort of shadow vector to kind of help you guide your eye and try to get aligned with this one. Okay, so I guess timer's up here. All right, so this one's different from the one that I gave you last time because these vectors are very close to pointing in the same direction. And it stands to reason that, you know, if they were pointing in exactly the same direction, there would be a problem. You really couldn't get to this orange vector at all. So if they're pointing in nearly the same direction, okay, you will be able to reach it, but there should be some kind of problem. You know, it should be an issue. You're not able to reach them if they're exactly parallel. There should be something sort of janky about the way that you reach them when they're not quite exactly parallel. And indeed, what you have to do, so if you just adjust these two modestly, you're going to be very much like pointing in pretty much the same direction as the first two vectors did. So if you want to get farther away, what you have to do is like really crank the weights. Like this one goes all the way to 10. That's going to give you a pretty significant component in the orange direction. In fact, pretty much the right component. And then you have to sort of cancel out all the part of the vector that was extending in this direction by cranking this one all the way the other way, and then you get them to line up. So you can see that the shadow orange vector matches perfectly only at this really extreme combination. So this, by the way, does have relevance for some things that we're going to talk about in data science and other applications. We're really going to want to detect this kind of approximate failure of linear independence in order to understand what's going on in situations like this, where we get solutions that have sort of kind of really extreme, in this case, not that extreme, but they're not all that close to being parallel. You can imagine if they were way closer, we'd have to crank these coefficients way more, and that's going to lead to various numerical problems. Anyway, we'll talk about that. This is kind of a preview. Okay, here's one more question from last time. Just kind of practice again and see what folks remember. So do the same exercise. I didn't put a code block on that. That's okay. You can pop open your code block here. Do the same exercise, but using numerical matrix algebra. So specifically using NumPy. So it should just be a couple lines of code. I suggest just typing like the digit 1 and hitting run so that your session will be launching as you code. And then when you want to evaluate something, it'll be ready. But in any case, see what we can do with that. Okay, lots of folks are really close. So I'm just going to give you a little more time to get a few more answers in. Okay, lots of folks are still close, but not a lot more answers are coming in. So I'm just going to leave it here for now. Oh no, answers suddenly started rolling in all at once. Yeah, so I'll share some of these. Yeah, nice job. This is right. Yeah, this one's right. Okay, cool. Folks are on point here. Just took a little more time. One thing though is a bunch of people, I didn't get around to pointing it out to everyone, but a bunch of people use the transpose of this matrix. So it's important that the columns of the matrix are the vectors that you're trying to linearly combine to get some result. So we're trying to combine 2, 1. That means the column needs to be 2, 1. So here I have the top left entry is 2, the bottom left entry is 1. If I wanted to space this out to be a little more kind of mathy, we might write it something like this. So you can see the first column is 2, 1, the second column is 1.9, 1.2. Uh-oh. Oh, forgot the dot lineage here. All right, and then we get our solution. Okay, so I want to address a question that came up last time that I like because I think it's really instructive. So you might be tempted to be like, oh, well, you know, I know what to do when I'm programming. I'm going to write a function to kind of encapsulate some logic, and then I can just call that function. And here we didn't do it this way. We didn't write a function like, coordinates of A, B, C, D, E, F that takes these 6 parameters and uses the LSTSQ function to produce a correct output. Why not? I mean, it certainly would work, but why is it not good style? Yeah, some great answers on the way here. So everybody's answer so far has been different and good. I'm going to share some of these if I haven't shared them already. Okay, so I took a moment to answer everybody's answer there because I thought they were really good, and I'm happy with this question because I can see folks are definitely thinking about this along some really good lines. So lots of good points here. Nick, do you want to talk about your answer? Yeah, exactly. The one problem is that the least squares function is already the function that we want. So this taps into this answer, which I think is really, this is a good piece of insight. If you write a function and it doesn't actually do any logic itself, it doesn't encode any logic, it just directly calls another function. You should just be calling that other function. You've introduced the complexity of an additional function and you haven't added any real functionality to your program. So there's almost no logic contained in this function, and that's not really a good sign. The other thing is it's not a good idea in general to be like constantly sort of going back and forth between entries and matrices. So matrices are more natural units of computation in almost all situations where you'd be inclined to use a matrix than the individual entries themselves. And if you're having to kind of extract individual entries to plug them into a function and then kind of repackage it back into a matrix, that's all kinds of bad. There's room for bugs. There's serious performance problems if you have a really big set of data that you're manipulating. It's really important to keep things in matrices and vectors to the extent possible. And this does the opposite of that. It's sort of like spreading everything out into individual Python objects where you could manipulate these collections of values together as a collection object, a matrix, or a vector. Okay, so let's move on to the next topic, which is going to be linear transformations. So linear transformations to me is where linear algebra starts to get pretty cool. I mean, you talk about like a vector spanning a line or two vectors spanning a plane. It's like, okay, you need those ideas. It's important, it's fundamental, but it's not that exciting, right? Like, we had a question earlier, like, what about spherical coordinates? There's lots of kind of cool stuff that you just can't really start talking about in a meaningful way just with all just flat objects in Euclidean space. And linear transformations don't get you all the way there. Of course, there's still going to be a ton of stuff that's not linear and is really interesting, but it gives you some dynamism. We're going to have pictures where things move in some way. And the reason is that linear transformations are, as the name suggests, maps. They represent relationships between linear structures, namely vectors, and we can visualize them by sort of drawing pictures in the plane or potentially in 3D space and sort of studying how they behave, and it starts to get more interesting. In any case, the main idea of a linear transformation, sort of in the stream of how we're developing things in this course, is that we're just going to kind of repackage our perspective on the matrix vector product. So if you remember, we defined the matrix vector product, A times X, to be the linear combination of the columns of A with weights given by the entries of X. But we can look at that differently and think of it as a function that takes X as an input and returns A times X, as previously defined, as an output. So that way we can sort of visualize what's going on. We can use the language of functions with inputs and outputs, things like codomain and domain and range, and we can get some insight out of that. So I'd say one of the most important ideas in this sort of basic in linear algebra, sort of up to eigenanalysis, where things start to get really cool. One of the most useful ideas is that you can take these very kind of basic ideas, linear combinations of columns of a matrix, for example, and kind of think of it different ways, put different visualizations to it, support it with different mental models in your mind that are mathematically equivalent but give you different insights. and your ability to sort of shift perspective is going to give you a lot of problem solving leverage. In any case, what we're going to do to visualize linear transformations is take advantage of the fact, not factor, that matrix multiplication is linear in the sense that if you multiply a matrix by a sum of two vectors, that's the same as if you multiplied them individually and then added. And same idea with scaling. And you can check this directly from the definition. It's a little bit dry. I'm going to skip it. I'm sure you'll believe me that the matrix product, the matrix vector product, as we defined it up here, will satisfy these properties. And incidentally, these properties are why we can't allow things that when we talk about vector spaces, we insist that they go through the origin. We don't allow sort of translations of planes to count as vector spaces. And this is related to that. So this linearity property, if we allow linear transformations to also translate in addition to actually multiplying, then we would end up with a class of transformations that doesn't satisfy these properties. So that's when we're always talking about things going through the origin and linear transformations have to fix the origin. That's why we want this linearity property. And we want to kind of separate out the translation piece in the situations where we do need it. Okay, so the thing is, once you have this basic property of linearity, it tells you that a linear transformation is actually specified by way less information than where it sends every possible input. So if I just tell you I have a function, I'm going to have to tell you where every possible input goes, or there's missing information. If I tell you, though, that it's a linear function or a linear transformation, then your life is simplified a lot, because as soon as you know we're just two inputs, I mean, there's infinitely many possible inputs. And if I tell you, let's say we're talking about on the plane, if I tell you where just two vectors go, if they're linearly independent, then we'll know where all the vectors in the plane go. And the reason is that every other vector can be written as a linear combination of those two. That's the point of a basis. And then we can use this formula, which tells you you can just distribute the A across. And here AV1, we've stipulated that we know where that goes. AV2, same thing. And so that tells us we can work out what this whole right-hand side is. And that tells us where this vector inside goes. So, you know, maybe it sort of makes sense. When you have this linear structure, if you know just very little information about the function, like just where two particular inputs go, that should be enough to recover kind of everything, because otherwise it would be kind of, you know, too floppy. It would be sort of too loose if you couldn't pin it down with just a little bit of information. So geometrically, what this corresponds to is oh, I think it didn't send because it took too long to render. Oh, no, it did. So now it's going to send twice. Oh, well. Yeah, so geometrically, what this corresponds to is the square grid mapping to a grid of parallelograms. So like the matrix 1, 0, 1, 1, 0, 1 maps this grid of parallelograms, or rather this grid of squares, to this grid of parallelograms over here. And the kind of key point when you're dealing with this particular picture, which I love and I'm going to use a lot, is that the columns of the matrix here are just the locations of the green and purple vector. If you just think about how matrix multiplication works, like the green vector is 1, 0, you multiply this matrix by 1, 0, it's just going to pick out the first column. The 0 is going to kind of wipe out this column when you perform the product. You're just going to pick out the first one. Same thing with purple. 0, 1 just picks out the second column. So I actually don't put any controls in this figure on the matrix entries. I leave you to do that by controlling this point. Like, for example, if we move this purple vector down here to 1, -1 approximately, then we're going to see those values appearing in that second column. So it's kind of a nice thing that there's a very clear relationship in the picture between what you're seeing for the images of the standard basis vectors and the entries of the matrix, which means you can just kind of play with this figure in whatever way you want and see any matrix that you want, and also kind of explore the space of possible transformations in a way that allows you to sort of, you know, leverage your brain's ability to perceive continuity. Like you can really see, like, between this transformation and this one, there's like one where it kind of squishes everything down, right? things that I think are quite a bit harder to see just in your mind's eye. Kind of helps to be able to grab it. Yeah, anyway, I just kind of wanted to talk through that without a timer running, because then I want to give you a chance to play with it. I'll give you a minute here. So use the figure to find the matrix which reflects every point across the line y equals x. So this diagonal line here, y equals x, there's a linear transformation that just flips everything over that diagonal. And I want you to see if you can use this figure to work out what that transformation is. By the way, you can move this text too if you want. Okay, let's move on. I think there are a few more answers coming in, but I've responded to everybody that's answered already. Yeah, so what we want to do here is swap the green and purple arrows. So if you think about like reflecting across y equals x, the purple one goes to where the green one is, the green one goes to where the purple one is. And we could figure that out from scratch, but we have the thing here, so we can just do it. Just swap them around. And oops, I put them the right way around there. Yeah, so this one goes here, this one goes here. By the way, you can hold shift if you're on desktop, you can hold shift to kind of zoom in, change the zoom, and get things a little more precise. But you can see, maybe if I rounded it more, it'd be more, even more obvious. It's 0, 1, 1, 0. Either way you read it here. The matrix of interest is this one. All right, that's because it takes the first standard basis vector and maps it to 0, 1, and the second basis vector and maps it to 1, 0. So you don't need the mathlet for that, really. The point is kind of, well, explore the question, but also gain some intuition as you drag these 2 points around for like, what does the space of linear transformations look like? Speaking of which, what are some different kinds of linear transformations that you can create using this mathlet? So we've seen one example, like a reflection along the line y equals x. What are some other generic terms like translation? Although translation is a wrong answer, that's why I chose that one. Don't want to give anything away. What are some things you can do with a linear transformation here? So I was fully expecting to need to explain the answer that lots of folks have given here, which is shearing. So this is I don't know. I mean, I guess you've seen it before. That's the point. This is not one folks usually know from grade school or wherever you learn about rotation and reflection and scaling. But yeah, no, this is a good one. Nick is saying identity transform. Yeah, that's important too. So the transformation which just leaves the input, returns the input with no modification. That's also a kind of transformation, and it's important that it is one of the things you can represent as a linear transformation. But yeah, we get all these other kinds too. And we get lots more besides those. So these are just kind of the basic kinds. So I'll show you a few of them, like rotation. Rotation, I feel like you sort of, probably pretty comfortable with that concept, just rotates the grid. Reflection is kind of the same thing, but it's going to swap the vectors around like this. So this is sort of a combination of a rotation and a reflection that I've shown here. You can just scale, you can just move the vectors sort of, further out. I guess I should leave them in the same orientation. You can also scale differently in the X and Y directions too, so it's not just a uniform scaling of all space. You can have a scaling that varies by direction. Projections, those are important. So if you align the vectors, then everything ends up on this line. So it's some sort of a projection onto that line. That's an important class of transformations. And then shear transformations, which is what we started with actually. So if I make this one go due east, and then I just tilt this one over, just sort of move it like that, I can get these kind of long, skinny parallelograms. But if you notice, it's still area preserving. Like the area of this square is its width times its height. And as I move it over, that same is true of the parallelogram. It has the same height and the same width. So these shear transformations are area preserving, even though they kind of like, make these parallelograms long and skinny. So they're in some ways they're kind of violent, and in some ways they're not inducing any change at all. So anyway, that's just kind of a brief overview of a few basic kinds of transformations. But one of the most important concepts here is that you've got lots of them that are not really that. Like, what kind of transformation is that? It's not a rotation because this angle changed. It's got some scaling, but it's just kind of funky. I mean, there's no single term that's going to describe what this is doing. It's really a combination of these various kinds of things. There's like some rotation, some shearing, etc. So these are kind of the basic types, and you can combine them in various ways to get lots of other kinds that don't really fall into any sort of pure group. Okay, so I'll just close with a question, and then we'll segue from here. We'll just pick up from here next time. What's the term in linear algebra for the dimension of the range of a linear transformation? Yeah, so the term for this is rank. So we'll get into this next time. We're going to talk about the rank of a linear transformation, which is just the term for the dimension of the range of that linear transformation. It's just measuring how much the linear transformation sort of preserves original directions versus like squishing some of them down to zero so that you end up with sort of a lower dimensional output. We'll pick up from there next time.